So let me know if you guys want to wait for some more time or we can start. Okay, so I'll probably start the session. So first, before beginning the session, I just wanted to inform you all that keep this session as informal as possible. You can ask me a number of questions if you have in between the session. So don't consider this session as a classroom session. You can ask any number of questions you have. Okay. So so Michaela already gave me the introduction, but I'll just introduce myself. So I'm Sanjay Vishwakarma. I'm a research software engineer at IBM. I'm also a Qubit advocate, and I'm also a founder of QuantumGrad. Today, we all are here for a quantum one-on-one session. So let's begin with a common question first. Why do we need quantum computing? So even if you ask your dad, like if you want to buy a smartphone or any device, your father might be asking like, why do you need this technology or why do you need smartphone? So let's begin with a simple question that why do we need quantum computing? So here's a simple question like how many ways I can arrange a dinner party of 10 people? So a lot of people might be knowing the answer of this. It's 10 factorial. And if you go on multiplying this, it will be 10 into 9 into 2, 1. And it is this many number of ways. Okay. So this is something like a simple problem that a classical systems might be able to like compute it in seconds or minute. But what if I keep adding chairs to this table? Like if I add one more table, it will be 11 factorial. But if I add one more table, it will be like 12 factorial, right? If I keep adding chairs to this table, it will grow exponentially, right? So if I add like 1,000 tables into this table, it will be like thousands factorial. And this is what our classical systems are still trying to figure out. So soon a simple problem converts into an exponential problem if we keep optimizing the things. So some problems are bigger than you think. But everyone might be thinking in the call that don't we have super powerful computers already available to handle these problems? For example, we have IBM supercomputer. It has this many number of bits to store, but which is still not enough to perfectly model a caffeine. Yes. So the caffeine only has 24 atoms, but modeling it requires a lot of power. Using classical systems, perfectly model caffeine would require 10 raised to 48 bits of storage. And in the entire universe, we have only 10 raised to 49 bits of atom. So clearly we have an issue, right? So some problems are too small to clearly see. Big and small. So this duality of big and small is exactly where quantum computing lives in. So classical computing, we all know that it follows the classical law of physics, but quantum computers follows the law of quantum mechanics. What do I mean by this is quantum mechanics? Quantum mechanics is nothing but how things behave on a really small scale, which is super weird. I'll be explaining how why. So quantum mechanics is nothing but just we go into really small scales in the atoms and electrons levels and see how things are behaving in that. Because of all these properties, quantum computers can tackle the really big problems, which are much more efficient than how a classical system handle the problems today. Now let's look at some another reason why I feel like quantum computers are super needed in this market. So we all know that machine learning and deep learning time is like training every they're doubling the training time every 3.4 months, and we also know that like we are also doubling the number of transistors every 24 months, which is also called as Moore's law. So if you consider this gap, which is 7x slower, right? If I keep doubling the training time, it either requires like if I'm doubling 3.4 months and if I'm doubling the transistor 24 months, there's a huge gap between that, right? So at this point, I have two possible solutions. One is like I can buy more NVIDIA GPUs, and what I mean by this is like suppose consider there's a model, there's a language model that I'm training it. Okay, I'm training it on a like suppose 1 GB of data. Okay, and it is taking 4 days. And now if I have the like more data, if I had 2 GB of data, so either with the current GPUs, like if I'm using 4 GPUs to train it and it's taking 4 days, if I want to train on 2 GB of data, I might have to like buy 4 more GPUs, like 8 GPUs to train that 2 GB of data. So either I have that option, like I can buy like more NVIDIA GPUs and train it and like burn more power and more expensive, and it's not a suitable option. Or the other option is to look for a powerful architecture which can actually compute a lot of this training power. And again, quantum computer seems to be a possible solution. One more reason. We all know that deep learning concept and machine learning concept was huge back in the decades, like it's what decades ago available, but how it came into existence, how it came into availability right now. So it was the hardware that made it possible and the availability of data. We have so many sensors, we have so many cameras today, and it all made data so much available that we are able to train models and get the output from it. But today we are generating 2.5 quadrillions amount of data, this much amount of data, how to process this much amount of data. If there is a business who wants to process this much amount of data and drive a decision within 1 day or within 12 hours, our classical systems cannot do right now. Clearly, we have an issue, right? So this is one of the another reason that I feel quantum computers seems to a possible solution to tackle bigger challenges. Now, why do we quantum computer matters to us? Though quantum computers today are limited in certain ways, the potential remain connected to it. It have like new paradigms to how we solve the problem right now with the classical systems. So quantum computer right now gives us new algorithms. It gives us new approach to problems, new technological breakthroughs. Now let's look at what is qubit and why it is special to us. So the name came from its description. It's a quantum bit of data. So the QU is taken from quantum and the bit is the normal classical bit, which we call it as. So it's just qubit. So it's a quantum bit of data, and qubit has special properties, which we'll be exploring next. There are few different ways in which we can physically make a qubit. It is similar to a concept of bridge, like they're all constructed with differently, but with some weaknesses and some strength, but they all serve the same purpose. Some of the example of building the qubit is so the IBM uses superconducting qubit, and there are different technology which is called ion trap. So there are like different ways how we can make a qubit, but it's more or less the same thing that we are trying to solve. So let's talk about the first property of qubit, which is called superposition. So imagine you have 3 coins in your pocket or in your table, okay? And in the world of classical physics, also known as our world, each coin can be in one of the states. So a coin can be head or tail, right? This means when you look at all 3 coins, they can be in one of the unique orders. So the 3 coins can be head, head, tail, or it can be head, tail, head, or any of the 8 possible combination, right? But in the world of quantum, also known as the size of atoms and electrons, each coin can be in both states simultaneously. And yes, yeah, each coin can be in the same place simultaneously. It can be head and tail. So the coins are in the superposition state right now, and they can be in the all 8 unique order at the same time. Let me explain this more. So now, the power of this is how in classical computer, if I want to look at 8 different states, I need to run the program 8 different time, okay, to see the all 8 possible combination. But in quantum computers, I only need to run my programs only once to see all the 8 states, and thanks to superposition. So given a number of qubits, suppose if I have 2 qubits, I get 2 raised to 2 raised to 2 states. So for n qubits, I have 2 raised to n states. And this is what quantum computers gives an exponential speed up, because we have that many number of states and we don't have to run program that much time. And we can represent a huge amount of data with less number of qubits. So let's talk about the second property, which is called entanglement. Remember how we said quantum mechanics can be weird in my previous slide, right? So even Einstein was surprised by this. He called this as a spooky actions at distance. So this is one of the weird thing, and it is hard to describe like what's going on, but what this essentially means is if you take 2 qubit and if you make it entanglement, they become correlated in such a way that even if we separate the qubit from like millions of distance apart, like even if I keep 1 qubit in United States and if I keep 1 qubit in India, when you observe one, you learn something about the other, no matter how far it is. So the other coin will also say me too. So one will be head and the other will be head or tail based on whatever the technique you're using to entangle the qubit. So this is one of the property that is extensively used in quantum computing. It is called entanglement. So just to recap, all the slides that I covered till now. So quantum computers use a special bit of data called qubit, which follows the law of quantum mechanics. We use all this law for our advantagement, enabling us to put qubit into superposition or to create entanglement. Using these qubits, it is estimated that a quantum computer would only require 160 qubit to model caffeine, which is much more manageable than 10 raised to 49. So before moving to on, if you have any questions between them, feel free to interrupt me in between. Okay, I'll keep going, but if you have any questions, feel free to unmute and ask. Okay. So let's talk. We talk a lot about what is qubit and what are the different properties of it. But let's look at how a quantum computer look like. The chandler. The quantum computers at IBM look like a chandler. It's full of cables sending for data and maintaining the environment. Very bottom, at the way bottom, you can see there is a quantum processing chip. It is very small. It is at the size of the stamp. But if you took a zoom look, if you just zoom into the quantum chip that I was talking about, it will look like this. The dark blue squares are the qubits, are quantum coins that I discussed in the previous slides. The squiggly lines you can see, right? It's the microwave resonator, which is how our coins are talking to each other. The computer is sending instructions to it. So these all squiggly lines are microwave resonators. And to completely work this all setup of qubits and the quantum computers, cables and all need to be kept at a very cold space, and it is 0.015 degree Kelvin. So we have to keep it at a very cold temperature to make all the quantum computers quantum computer work properly. So to maintain this temperature, you won't be seeing like quantum computers lying outside, like in just lying outside or anywhere we have kept open. No, to maintain this cold temperature, you can see this dilution chamber is there. So this white, it will be always enclosed in a chamber because we have to keep it cold. So this white thing you can see, right, the outer covering, it's a dilution chamber that we use to keep the quantum computer cold. And yeah, and this person is a research scientist IBM, Nick Barron, and I guess he's also delivering a talk to your session, maybe I think 1 or 2 days afterwards of me. So this is Nick Barron. And so you might be thinking like, if quantum computers need to be placed at so much cold temperature, then how it is accessible to us, like how a normal person can access it. So it is accessible via cloud. And this is one of the small video to demonstrate like how we at IBM are able to demonstrate a quantum computer. So from classical system, you build a circuit and you send this circuit to the IBM systems. The IBM systems convert your circuit into pulses. These pulses are then given to the quantum computers, where the quantum processing chip processes your circuit, and it again gives back the results in the form of pulses. These pulses are again then given back to IBM systems. The IBM systems then convert your pulses into an output that a classical systems can understand. And this is how it is displayed on your classical system. So this is one of the way that we at IBM do to make quantum computer accessible to you via cloud technologies. So let's talk about like some of the futures of quantum computing. Like there's a lot of hype in the market, but where quantum computers will be used, actually we'll be seeing it now. So these are some of the future of quantum technology, like the areas where quantum computers will be used. It is not limited. We have more applications, but in a slide I have just put 6. So one is the finance optimization. So there's a lot of banks right now who are doing a lot of portfolio optimization, like fraud detection and all sorts of using quantum computers. And one of the bank that is recently publishing a lot of papers is the JP Morgan. So if you are interested in looking into some papers, you can go ahead and just check the archive for JP Morgan. They have a lot of portfolio optimization done by using quantum computers. So yeah, in finance, we are able to like do a lot of portfolio optimization and detect whether customers will be doing a fraud or not. And then there is a random search array. So what I mean by this is, suppose there's a huge database, it has 1 million records in it. And if I want to find an element in it, so in a particular column, so how I'll be going towards it, I'll be just doing searching in the column, and it will be like O of n time complexity. But somewhat might say like you can use indexes in database. So even if I use indexes, the time complexity will be still log n. But in quantum computers, if we use to search an element in a database, we can use it in O of root n time complexity, which is quadratic speed up. And there is an algorithm, specific algorithm for finding an element in one shot. It is called a Grover's algorithm. So in big data, and we have a huge applications on that to find the data in one shot. Then there is chemistry simulation, where we are able to like do a lot of optimizations in that. Like we are able to simulate the molecules which are used in chemistry, and we are it can be like, you can consider this as a drug discovery as well, where we are able to do a lot of optimization, like take small amount of this medicine, take small amount of this medicine, and make a medicine and see how it is acting on humans. So we can like generate a lot of possibilities, like yeah, this is the combination, and we can find out whether this medicine will work or not. So chemistry can be correlated to the drug discovery. And then there is machine learning, which is one of the hottest field right now, because we have a lot of advantage on using QML. So there's a training field that is called as quantum machine learning, where we are able to run different where we are able to run different machine learning models on quantum computers right now. So quantum machine learning is one of the hottest future right now. We are seeing a lot in that. And there is a lot of Qiskit has textbook. Qiskit textbook has one chapter on it, and there is a lot of other people also who has done a lot of interesting work in quantum machine learning. Then there is encryption period finding, and this is where the people are talking about where RSA algorithm people are thinking they might be able to break. Sorry, where people might be able to break. So we're just able to like find a period D in that, because based on the Schwartz algorithm, because we are able to factorize the number, which is nearly impossible for the classical systems to find. But using Schwartz algorithm, we are able to factorize the number, and that's where all encryption and things are coming up. Where US recently announced the encryption standards and all sort of things. So there's a lot of stuff going on the encryption and security side of quantum computers, where people are trying to make their security of the data to be very strong. So there is a terminology called quantum safe, where a lot of industries are moving towards quantum safe zone, because they want to make their data secure once the quantum computing comes into picture. So there's a lot of terminologies that you guys will be hearing, like quantum safe, quantum advantage. There's a lot of stuff coming up. So yeah, that's what the encryption is there, where we are able to like encrypt the data much securely than the classical RSA one that we have right now. And then there is a last application which is called optimization in quantum tunneling, where we're able to optimize a lot of stuff, and we're able to simulate a tunneling effect. So this was all not limited. It is a limited slide for the future of quantum computing, but we do have a lot of applications more. And let's look at some of the quantum gates. So similarly to classical systems, how classical systems have gate, right? XOR, X gate, NOR gate, AND gate. Similarly, we also have a quantum gate. So it is nothing like rocket science or something that quantum computers are different. No, quantum computers are also pretty much similar to classical systems. It's just the way how it works is different. So one of the gate I want to talk about is the poly X gate. It just flips a qubit from 0 to 1 or vice versa. And the second gate I want to talk, and poly X gate is pretty much similar to the NOT gate that you guys have in the classical systems. So it's just the name is different. So it's a poly X gate we call in quantum computers. The second gate is a Hadamard gate. It just puts a qubit into superposition of states. So since I talked about superposition, right, 0 or 1. So if I put the edge gate in front of a qubit, which is in 0, and all qubit starts in 0 state. So if I put a edge gate and in front of a qubit 0, it will be in a superposition of 0 and 1. So to put qubit in superposition, we use this Hadamard gate, edge gate. And there is this last gate, which I want to talk about, is control NOT gate. So it only flips the second qubit, only the first qubit is 1. This is pretty much similar to the classical gates that we have. So in quantum computers, it's like same terminologies we use as the classical system, but it's just the functioning and how the circuit will be behaving is different, because we go into more into atom and electrons level. And we have so the classical system is just built out of bits and using transistors, but in quantum gates it is all built off using qubits. So it's just a technology that has been used different, and we're able to harness the power right now. So whenever you're learning any programming language, right, Python, Java, or anyone, like any language, every language has the hello world program, right? So in quantum computers, we do have a hello world program, which is called as bell state. So this bell state is one of the specific example of the two qubits, which represent the simplest example of quantum entanglement and superposition. The edge gate first, it puts the qubit 0, qubit 1. I mean, qubit 0 is the first qubit that is called Q0 into superposition, and the C0 gate flips both or does not flip both based on what is the input on the qubit 0. Assuming that the qubit starts from 0 state, when you measure, they will be in the 0, 0 or the 1, 1 state. So based on this circuit, the output will not be anytime 0, 1 or 1, 0. It will be always 0, 0 and 1, 1 because of the entanglement and superposition. And so this bell state is the hello world program in quantum computers that will be coding out in next session in 5 minutes or 1 minute. Yeah. So yeah, I'll be moving out to the live demo session where I'll be coding out this build state. So before moving to the coding part, I just wanted to ask if anyone have any questions before all the slides that I covered, so I can answer that question before moving to the coding session. Or if you don't have, like, I can just move. Feel free to unmute yourself and ask any questions if you have. So I'll just go here. So there are a couple of ways in which you can actually access a quantum computer. So one of the easiest way if you want to do it is the IBM Quantum Experience. And whatever resources and whatever information that I'll be sharing now, it will be all public. So it's not something that I have access to this and I can only access it. Whatever I'm showing, it's open to all. Anyone can access. So one of the simplest way to use the IBM Quantum computer is to go on the IBM Quantum Experience, and you can just launch a lab here. But provided that you need to first sign in out in this to provide authentication and all. So here you just need to click on new file, and you can just select a Python 3 file, and yeah, we have a Jupyter notebook here. And there is like a couple of other ways also where you can use this quantum computers. Qiskit is you can install locally as well. I think I'll just show it that also. So if you don't want to use the IBM Quantum Experience, you can actually download Qiskit as well, where it's a Python package. Yeah, so you can use Conda as well to create, I think, to download the Qiskit library, and you can also do a pip install as well. So there are a couple of ways in which you can use the Qiskit library. One of the simplest ways to go to IBM Quantum Experience, and you don't have to worry about a lot of dependencies that you want to download. So how quantum computers are accessible and which programming language we use. So it's not something like a new programming language that you guys need to learn about quantum computers. It's the same Python that you use. So you need to know only Python language for accessing quantum computers. So suppose if you are, how you import in a Python, like if you want to use NumPy, you import like this, right? Import NumPy as NP. We do, if you want to use module in Python, right? We do like this, right? And if you want to create a list, we just do list is equal to we created a list, right? And if I want to just add one element, what I'll do, I'll just use a dot function, and I'll just do append, and I'll just add one more element to it. And now if I want to print it, it's done, right? So this is how a basic Pythons we use, right? Like this is all basic Python. So these are the same things that we'll be using in building quantum computers. So that is pretty much similar to how we do in Python things. And you'll be seeing how I'll be using these all functions in actually building a quantum computer. So it is pretty much same. So from now, I'll just import whatever I'll be needing from the Qiskit library. So Qiskit is a module that we use for which has all the functions like NumPy, how you use NumPy, because NumPy has all the functions built and you have to code less, right? And you use some library. So similarly, Qiskit is a library that we IBM have to access quantum computers. So from Qiskit, I'll just import star. I'm just importing all the stuff from there. And now I'll just build the quantum registers. So I'll be using two quantum registers, since in the circuit diagram I showed, right? I'll be using 2 qubits. So it's essentially 2 qubits, which I'm calling as quantum registers. And since I mentioned in the previous diagram how quantum computer is accessible, you will be sending your quantum circuits, and the output will be again given back as a classical output, right? So we need a classical register as well to get the output. So I'll be taking classical register here. Now, if you want to build a quantum circuit, you just need to so we have a lot of functions, which is you can just use it and pass parameters to it, similarly to Python. So we have a function called quantum circuit. If you just pass your quantum circuit and quantum classical registers, it will be made. And whenever you are coding this quantum computers, at any moment of time, if you feel that you have to see your quantum circuit, how it is looking like, you can always do qc.draw at any moment of time in your Jupyter notebook. And you can see the quantum computers is looking like this. So it has we made two quantum registers. It is Q0 and Q1, and we have two classical registers, QC0, and it is like two classical registers for taking the output of quantum registers. So now, since in my first diagram, I just add a Hadamard gate in Q0, right? I'll just do qc.h. So this is again the same dot function that you all guys use in Python, and H stands for Hadamard gate, and I'll be putting on qubit 0. So I have to put 0 here. So now again, if I want to see my circuit, how my circuit is looking, I can always do qc.draw. So now you can see it was pretty similar to simple like how we do the functions in Python. It was simple to do in quantum computer as well. You need to do the dot function, and you need to put the gate and the number of on which qubit you have to put. You just have to write that. So it's qc dot h 0. So 0 stands for qubit 0, and we have added the header mod gate. Now again, I just need to put the CX gate, and CX gate stands for the C naught gate. And again, the control qubit is 0 and the target qubit is 1. So CX gate is applied now. Again, I'll do qc.draw to see my circuit, how it is looking like. So yeah, you can see I have put the C naught gate as well. You just need to do the dot function and the name of the gate. And now I have to take the measurements of 2 qubits on my classical register, right? So I need to do qc.measure for that. And in measurement, I need to pass the quantum registers on classical registers. So again, I'll just do qc.draw. And yeah, so I'll be taking the Q0 result on my C0. I'll be taking the Q1 result on C1. And then, so there are a couple of ways, like I can directly send this circuit to the quantum computer as well. But what we do is like, since quantum computer is not like it's accessible to everyone, but since the circuit goes into queues, and it is not something like if you send a circuit, you'll be getting the result back quickly, since it's a public machine that is available. So there is a simulators that we use, like you can actually validate your circuit, whether it's a correct circuit or not. So we have a simulator which will simulate your quantum circuit and tell you like whether this is expected results or not. So what we do before sending the circuit to the actual quantum computers, we run this circuit on a simulator and see that a circuit is we just verify if the circuit is correct or not. If there is some mistakes on the circuit, we can improve it before giving to the quantum computers. So what we do is we can just take a backend. So AER is the model that provides us the backend. And the name of the backend is AER underscore simulator. So, and if you want to just run the circuit on simulator, we have a function called execute, which takes parameters like quantum circuit, which is RQC, and again we can give backend. And our backend is in this. So this execute parameter just executes a quantum circuit and stores the results in job. And if you want to take the result out of it, you can take it from job.result. And now if you want to view the result, what is the actual result of my quantum circuit? We have a model from Qiskit. Tools, visualization, import, plot histogram. And in plot histogram, I can just pass my result and get counts from it. So now you can see my quantum circuit, as I mentioned, the result will be 0, 0, and 1, 1. Since the qubit 0 is in superposition, it has 0 and 1 coming up. So when it is 0, the qubit, the qubit 0, the qubit second qubit that we have, it will be 0 only. So the result is 0, 0. But when the qubit 0 is in superposition of 1, the output will be the second qubit will also be changing to 1, and it will be 1, 1. So the output will be always 0, 0, and 1, 1 because of superposition. It will be like never 0, 1, or 1, 0. So since I'm like confirmed that, this is my circuit is ready and it doesn't have any error, I can send this circuit to an actual quantum computer. So below are the steps like I'll be using for actually sending this circuit to the quantum computer. So you just have to do ibmq.load account. So what this step is doing is it is taking your credentials, authentication token, and which will be used to provide you the quantum computer. So in this case, we need a provider. So we can do ibmq dot get provider. And in this case, our provider is IBM Q. So again, we'll repeat the step. Again, we have to change the backend. Since the earlier backend we use is a classical simulator, now we need a quantum computer simulator. So I'll just do provider dot get backend, and I can take any quantum computer. So we have a lot of quantum computers on the cloud, and I can use any of them. So I can use IBM. So I've just taken any quantum computers available. So this is just the name of one quantum computers that we have in IBM. And again, if I want to send the job, I can again do execute, same process that we use for running on a simulator. I can put my quantum circuit and I can put backend equal to again backend. So now this job has been sent to the actual quantum computers, but it is not executed like on the same spot, because I told that there's a queue mechanism. So a lot of people are accessing the quantum computer right now. So what we do is like we take the jobs from all the people, we make it on a queue, and then based on the queue, one by one, we process it. So if you want to see like what is the status of my job, like where in which number of queue it is and whether it's executed or not, we have a model for it as well, where you guys can use and see what is the status of it. So you can just do qiskit.tools.monitor. You can do, and this job monitor, you can pass your job here, and you can see the job status right now is queued. So and this dynamically changes, you don't have to run multiple times. So right now your circuit has been queued to 40 numbers. So it will take a lot of time, not a lot of time, like based on how the people in front of you has submitted circuit. So they will be executed first and then you will be executed. So this is a public quantum computers available. So save some time. I won't be like waiting for 40 to run. So I have just run my circuit in a backup session where I have taken the result. So this is the same circuit that we built out and everything is same here. So, so once your job has been successfully sent and it's completely done, you can see the status changing to job has been successfully run. So again, I'll be doing result. I'll be taking the results from the job, and again, I'll be doing job.results for it. And again, I'll be using the plot histogram to see the results. And this is the result. Now you guys might be thinking like, since you mentioned like the result won't be 0, 1 and 1 zeros, and why I can see this on my histogram. So this is something that I want to talk about is the quantum noise that we have. This is one of the challenges that we have right now. So quantum computers, since I mentioned, right, they are limited in certain ways, and this is one of the ways that is limited. So quantum computers right now are not perfect, but running the circuit multiple times, we can easily make out that the result is 0, 0 and 1, 1. So based on the probability, like this is 47% and this is 47% and this is like 0.2%, 0.3%, I can easily cross off this. I can say that yeah, 0, 1 and 1, 0 are not the actual result that I want. The actual result is 0, 0 and 1, 1. So this is something that you'll be seeing extra in quantum computers. This is called as quantum noise that we have right now. And this is one of the challenges that we have. And there's a lot of active research going on in this. It's quantum error correction code. So it is again one of the hottest topic right now to find a lot of quantum error correction codes. Similarly, we in classical computers also we have a lot of error correction code. If you guys know about it, similarly we are trying to implement something in quantum computers to minimize this sort of errors. So this is one of the challenges that we have right now, and yeah, but running the circuit multiple times, we can easily make out from the probability like yeah, 0, 0 is the result and 1, 1 is the result, and we can easily ignore 0, 1 and 1, 0. So this was some of the like live session I just want to take about, just wanted to give about a brief session about how you can run a circuit on a simulator and how you can run on the quantum computer actually. And yeah, so I would like to talk about one of the myth that we have right now. It is called that a lot of people are talking about like quantum computers will be replacing classical systems. It is not. It's nearly impossible. Like quantum computers will be replacing classical systems, not even in future, or not even in near future or any time, because you know the quantum computers are special purpose quantum computers. It is not something that will be used for writing Word documents or doing a calculation or something. You won't believe if I give 2 into 3 to multiply this 2 into 3 and the answer is 6, right? If I give this simple operation to classical systems, it will be giving me results in microseconds probably. But if I give 2 into 3 to a quantum computers, it will perform worse than a classical systems as well. So quantum computers are something that will be used for special purpose, like for special applications where a classical systems cannot solve that problem. So in near future, quantum computers will never replace classical systems. It is something that convergence of technology will happen. So the future is bits plus qubit plus neuron. So it is not something like only qubit will be winning the race. No. Since you saw in the circuit, right? We need classical qubits as well, classical bits as well for the circuit. So the future will be convergence of technology. It will be like the neurons from the AI. It will be plus the qubit plus the bits. So it will be all three together working towards solving a challenge. And this is something that it's coming up in the picture. So we have a quantum serverless that is coming up where we are adding additional layer to it. So if you give a task to us, like, yeah, this is the task you want to run. So we'll be like dividing the tasks into multiple chunks, and some of the chunks will be processed by classical systems and some of the chunks will be processed by quantum computers. So all the technologies will be working together to solve the challenges, and not even like one technology running ahead and winning the game. So it will be all three will be working together. And lastly, I want to say anybody can learn quantum computers. It is not something that I can only learn quantum computers. You guys cannot learn. No, none of the background matters. Even if you are from so consider an example. Okay, so if I'm a physicist, okay, I can build quantum computers, but where I can use quantum computer? Who will be telling me? I need people from finance background to tell me like, yeah, this is the problem that I'm facing, and I need a quantum computers for this. I don't know like how finance people do things, right? I need people from finance background. So similarly for chemistry, if I build quantum computers, I need people from chemistry background to tell me like, yeah, how to do some molecule simulation and how to use quantum computers to have a quantum advantage. So there's something like everybody can learn quantum computing. It is not something rocket science that people have made. It is something that everybody can learn quantum computers, and we need a lot of community to solve the quantum challenges that we have, and to have a potential quantum advantage today. And these are my contact details. But before closing this sessions and opening floor for the questions, I do have a talk. Want to talk about QuantumGrad. So, right? QuantumGrad is nothing special, something, but it's a one-stop solution where one can have all the quantum information. Right? There's a lot of things going on, hackathons going on, news going on, publications going on. But how to keep up to date with that, and how to learn quantum computing, or just want to stay updated with quantum computing, or if I want to learn something. So QuantumGrad right now is a global contribution platform where a lot of people come and write articles on it. So there is a lot of articles here. You can see a lot of people has written a lot of articles. So you can just come here and browse a lot of article where people write introductory article, complex articles as well. And so you can just click on the right button, and right, it's one of the best way to just memorize the thing. Writing is one of the best way to get used to a technology or get something memorized. So you can always, if you're learning something new on quantum computing, just come here and write, and your writing will eventually help society to help different concept. It is not something like you're also memorizing, and it's like other people of community are also getting benefited from it. Similarly, there's a lot of news is coming up. We have all the quantum news is here. And similarly, if there is publications, we have all the publications of quantum computing coming here. And there is event section as well. This is one of the pain point that people are not aware of the events that are happening. So people can come here and publish their events, and you can browse all the events that are happening all across the globe. And if you're looking for internship or jobs, this is again a platform you'll be seeing a lot of openings all over the globe for postdoc positions, for full-time internships. And there is a book section as well where there's a lot of books on quantum computing. And similarly, we have our YouTube account where we make a lot of video on quantum concepts. So we have a developer series as well where IBM has their developer certificate, right? So we just make sure we are just making it all free of cost. We just make a lot of videos there. Similarly, we have our Instagram account where we make a 1-minute reels about different quantum computing concepts, and we post a lot of information of quantum information here. So yeah, and we also have a newsletter. So if you want all these contents of the website coming to your mailing box, you can just go ahead, just sign up right now, and you'll be all good to go for the newsletter, and you'll be receiving on a weekly basis all this information on your mailbox. And yeah, I spoke a lot. So this was all about the today's session. And now I'm opening like floor for all the questions that you have and I can answer. I can see some of the questions on the chat. Like Nathan is asking how fast can information be transmitted with quantum techno entanglement. So one of the thing is Nathan, like so if you are thinking about like teleportation from using quantum computers, is right now it's not possible. Like we cannot send information from one place to another place using entanglement. But it is some like if you are thinking in terms of quantum teleportation, it is not possible right now, and I don't think so. It's in near future also it will be possible, but it's something that we use in quantum circuit to pass one state to the another state and to see what will be the another state, because there's something that we use in circuit and it's not something that will be used in quantum teleportation, if that you are meaning to say. So you can feel free to like unmute and ask if I don't answer your question. Jan is asking, is the quantum machine learning free to use? Yes, quantum machine learning is free to use. So actually the quantum computer is free to use. So you can actually use quantum machine learning. You can also do quantum NLP. So there's a lot of stuff that is coming up in quantum. So it's just the quantum computer remains the same. So it is open publicly. So you can run quantum machine learning also on quantum computers and everything. So quantum machine learning is free to use, yes. And yeah, let me know if you guys have any questions. Like, you can feel free to unmute, and if you have any questions on the slide, also I can take. I have not kept this session a lot, too much advanced level. I just wanted to keep it as a basic and small and sweet. So, can you explain why some operation could be slow on quantum computer compared to classical computer? So, the reason why it is like because we do a lot of operations, right? The qubits are maintained like for superpositions. Like every qubit has a property of entanglement in qubit. So if there is some operation that I don't need a super for a qubit to go into superposition, like if I just wanted to um, multiply two numbers, like it's just like a bit of, if you convert two or three into binary numbers, it's a bit operation, right? It's simple operation. Why do you need to like go into a superposition state, create into superposition, and then do multiplications? And it is something that in quantum computers and quantum circuit behave separately, like differently. The qubits are not just to take 1001. So if you need something like just multiply 2 into 3, or the word document that also we use, at the end what boils down to 0 1, right? If we have some operation that can easily be done by just performing some operation on 0 to 1, we cannot like go to superpositions or something, because it's all time consuming process, and we need to actually properly encode and decode the circuit properly. It is not something that there is a data, like if I have a data set, I can just give it to quantum computers. No, we need to properly like analyze the data, encode it properly, like it will be digestible of the quantum computers and the quantum circuit also. We need to properly see like if we are able to transmit the data properly from one end to another end, because qubit is something that loses its property. It's not something it's remained superposition throughout the circuit. No, it is something that it loses property. So from that moment we need to like properly extract the output and give it to the another stage of the circuit. So it's a bit complicated, like how quantum circuit we can actually use to perform some operation. So these are some of the reasons that quantum computers is slower than classical systems, because the way it works is different. It is the operation that we perform by the qubit by a bit is different here. And Michaela has already sent a good documentation in machine learning. So Qiskit has a, if you guys are interested on like quantum machine learning, right? Go ahead and like take a look on Qiskit. Qiskit documentation is one of the best resources out there. And if you have any questions, you can like you can just mail me over the my email ID here, or you can connect me with LinkedIn. I'm open to ask any of answer any of your questions. Yeah, and yeah, I think that yeah, I think chat questions are already answered. And let me know if you have any questions about quantum computers or QuantumGrad. I can answer both.
Okay, well, I think if anybody has no more questions, then Sanjay, thank you so much. It was a really great intro to Qiskit, and I think showing everybody all the modules.
Yeah.
Just so everybody knows, we'll also be going over getting started with Qiskit and setting up an account in one of our workshop sessions, I believe on Thursday as well. So we'll make sure you guys know how to use them. I posted the links to QuantumGrad in the Fall Fest chat as well, if you want to check out the website. It's super great. I actually use it quite a bit. I think like Sanjay said, there's tons of internships on that website too. And I think it's just a really great resource to bookmark. Yeah, so if everybody has no more questions, then Sanjay, thank you so much for being part of the Fall Fest at UT Austin. It was really great to have you.
Yeah. So yeah, guys, thank you for having me. Have a nice day and enjoy the rest of the fall.
Thank you so much. Have a great day.
Bye.